Picture this. You're running a massive green energy plant, but here's the catch. Every single piece of physical machinery in that plant directly dictates your financial profitability. Welcome to the world of biomass energy. It's a fascinating space where engineering realities and the balance sheet are just fundamentally linked. I mean, if a conveyor belt jams or a boiler corrodes, your margins don't just shrink, they can disappear entirely. Okay, let's dive into this explainer and unpack exactly how the physical realities of biomass translate into hard financial data.
Here is our roadmap for today to show you exactly how to keep a plant like this running without losing your shirt. We're going to cover 4 parts: the biomass base load advantage, from field to grid, the financial equation, and finally, guarding the bottom line.
All right, Section 1, the biomass basal load advantage. Before we can really master the financials here, we have to deeply understand the core product we are actually selling to the market.
When you hear renewable energy, you probably immediately picture solar panels or wind turbines, right? And those are fantastic, don't get me wrong, but they come with a massive caveat. Their fuel, the sun and the wind, is completely free, but the power generation is intermittent. It just stops when the sun sets or the wind dies down. Biomass, well, it's the exact opposite. You actually have to pay for the fuel, which is organic waste, but in exchange, you get to run your plant all day and all night, totally regardless of the weather.
And that brings us to the concept of baseload power. Baseload power is that highly reliable, constant, 24/7 energy foundation that entirely stabilizes the national electrical grid. Because a biomass plant operates a lot like a standard thermal power plant, burning organic waste instead of coal or gas, it provides this highly sought-after stability. This specific capability is an absolute superpower for grid operators. It makes your plant incredibly valuable and guarantees a constant demand for your electricity. Moving right along to Section 2, from field to grid. Let's move to the physical side and see how this builds, tracking this organic waste from the dirt all the way to the transmission wires.
So we can break down the whole biomass to electricity process into 5 really distinct technical stages: sourcing, handling, the boiler, the turbine, and finally, grid interconnection. Now, if you're the finance director, you need to look at this not just as some engineering diagram, but as a financial pipeline, because every single one of these 5 steps carries a direct, undeniable financial consequence that is going to hit your bottom line.
Let's look at steps 1 and 2. This is all about securing your fuel and prepping it. Most successful projects use what's called a farmer-dealer-plant model. Basically, dealers drive around collecting agricultural residues. We're talking rice husks, corn stalks, forest debris from local farmers, and then they haul it to your plant. Once the fuel arrives, it moves along conveyor belts, but it absolutely must go through intense filtration. You have to filter out non-combustibles, sand, stones, stray pieces of metal. If you don't catch that stuff, those foreign objects will physically block your feeding mechanisms and just literally tear your equipment apart.
But you know what the real silent killer is in the sourcing phase? Moisture. Before you can use the feedstock, it almost always requires dehumidification, drying it out, because high moisture content absolutely destroys the heating value of your fuel. From an executive point of view, if your feedstock isn't dried properly, its energy density just plummets. You have to burn significantly more fuel just to generate the exact same amount of power. Think about it. If you're buying your fuel by weight and it's wet, you are literally paying for water. That is a massive, immediate drain on your profit margins.
Okay, step 3 is where the magic and honestly the danger happens: the boiler. The biomass enters the boiler for direct combustion. Plants usually use either grate-fired systems, where the fuel burns on a moving floor, or fluidized bed boilers, where air actually suspends the fuel for highly efficient burning. The massive heat from this turns water in the boiler pipes into high-pressure steam. But there is a severe technical risk to watch out for here: corrosion. The unique chemical makeup of organic biomass degrades boiler surfaces way faster than traditional coal plants. It's a massive maintenance hazard. Once we've got that high-pressure steam, we move right into step 4, the turbine and the generator. The steam is blasted into a steam turbine, and here the thermal energy is converted into mechanical energy as it spins these massive turbine blades. The turbine is mechanically coupled to a generator, which then converts that rotational energy into alternating current, or AC electricity. Pretty standard power generation stuff, really, but it relies entirely on that steady steam pressure from the previous step.
Finally, step 5, getting all that power out to the world. You can't just plug the generator straight into the national grid. The voltage is way too low, usually around 400 volts. So it runs through a step-up transformer to boost the voltage to something like 115 kilovolts. It passes through substation switchgear and circuit breakers designed to protect your plant during grid faults. But the single most important piece of equipment for you, the finance director, the accountable metering. This highly calibrated meter measures exactly how many megawatt hours are delivered to the grid. The second power passes that meter, it triggers the payments under your power purchase agreement. That's the exact moment electricity officially becomes revenue.
Section 3, the financial equation. Now, what's really interesting about this next part is how we pivot from the factory floor directly to the balance sheet, looking at the actual numbers that make this whole engine run.
When we model biomass against something like solar, the capital intensity is honestly jarring. Biomass demands high capex, capital expenditure. Why? Because those complex, highly engineered boilers and strict emission systems are incredibly expensive to build. But it definitely doesn't stop there. Biomass also requires high OPEX, or operating expenditure. You're constantly buying fuel and paying for labor. Compare that to a solar farm. Solar generally has lower capex and extremely low OPEX, simply because the fuel is free and you don't need dozens of people standing around watching panels soak up the sun.
Let's drill down into those variable expenses for a second. You might think the organic waste itself is your biggest headache, but actually, scratch that. Logistics, literally just the physical transportation of this bulky waste, can easily eat up a staggering 30% of your total variable expenses. That heavily impacts your gross contribution margin, meaning you have way less profit left over to cover your fixed costs. It makes the physical location of your plant arguably the single most critical strategic decision you're ever going to make.
And then we have the human element, 85. That is the typical number of full-time equivalent staff required just to run a standard large-scale biomass facility. Think about that OPEX requirement. You need a small army to manage fuel handling, continuously monitor the boiler health, ensure environmental compliance, and maintain all those complex moving parts. It is highly labor-intensive, day in and day out.
Now, on the revenue side of things, your baseline income is secured via your power purchase agreement, or PPA. But remember that baseload advantage we talked about? Well, if your plant goes down because of boiler corrosion or a fuel shortage, you don't just stop making money, you actually get hit with availability penalties from the grid. This downtime directly hits your CFADS, your cash flow available for debt service. And if your cash flow drops, you risk breaching your bank covenants. Luckily, there is some upside. You can boost your income through ancillary revenues. Things like selling biochar, which is a byproduct used as fertilizer, or monetizing renewable energy credits, better known as RECs.
So, we know the physical risks, and we know the costs. Section 4, guarding the bottom line. Let's go through the ultimate checklist for financial survival in the biomass business.
Think of this as your cheat sheet. It maps the physical plant risks directly to their financial solutions. First, if wet fuel is delivered, you absolutely must verify the gate price standards. Implement rigorous moisture measurements right at the gate so you aren't paying for water. Second, audit your grid deductions. Make sure your forecasts account for a typical 5% grid admin fee so you aren't overstating your cash flow. Third, lenders almost always demand a 95% availability target, meaning your plant basically never goes offline. To hit that, verify your budget fully funds those 85 full-time equivalent staff. You cannot skimp on maintenance labor. And finally, feedstock price spikes. You have to check how your contracts are structured. Are they fixed or are they indexed to a benchmark?
So the crucial point is this: unlike solar, your fuel costs can and will change. If your feedstock contracts aren't firmly capped, extreme volatility in the local agricultural market will absolutely destroy you. Listen to this: just a 15% spike in the price of local agricultural residues can take a highly profitable project with a projected 30% internal rate of return and turn it completely negative, overnight. The financial success of a brilliant engineering marvel can be entirely undone by just one bad harvest in the local county. Crazy, right?
At the end of the day, biomass is an incredible feat of engineering. I mean, it literally transforms waste into continuous, reliable, grid-stabilizing energy. But it's a heavyweight operation, demanding constant logistical, technical, and financial vigilance. Which leaves us with a really critical question to ponder as we look toward the future of the whole renewable energy transition. Considering the intense operational costs and those volatile fuel markets, is the reliability of baseload biomass truly worth the financial risk? Thank you so much for joining me on this explainer, and as always, keep questioning the mechanics behind the numbers.